The second video lecture I'm going to do here is on the early gas laws. So now, besides just understanding the variables and knowing what pressure, volume, temperature are, how are these variables related to each other? And this video should be watched after you have completed the Exploring Gas Behavior Station lab. I'm going to talk through that lab as an experience to then set us up for how to do math with the gas variables. So this is your whirlwind through the early gas laws, looking at our variables of pressure, temperature, and volume. How are they related? So in station 1 of the lab, where you had the 2-liter bottle, which you then squeezed and looked at how a test tube rose and fell, what you were really looking at was looking at increasing the pressure and then seeing volume decrease. So that little test tube that you had trapped gas, and then you had the water in here, and this line for the water, it went up and down depending on if you squeezed it. So the gas particles, which were trapped in there, then could go up, or it could even spread out. So then when you squeezed the bottle and increased the pressure, the line moved up, and so the gas particles occupied less space. And a mathematical relationship for that, if you look at pressure and volume, and when you increased the pressure, the volume kind of went down, and vice versa. This is called an inverse mathematical relationship. As one variable goes up, the other goes down. So if pressure decreased, the volume increased. So when you let go of that bottle, okay, that this was sitting in, then when you let go of it, this line decreased down, and then the bottle rose back up. And that's due to the buoyancy of the test tube in there. It's designed to float, and then when you increase the pressure, you decrease the volume of the trapped gas, since gases are compressible, which then forces more water into the test tube, and then that creates the test tube to sink. Mathematically, we can express this relationship in an equation. So this is the first mathematical equation that you're going to see. It's called Boyle's law, after Robert Boyle, who kind of discovered this relationship between pressure and volume. And it says P1 times V1 equals P2 times V2. And really you want to think of this as P1 and V1 are like your initial conditions, and P2 and V2 are the final conditions, okay? Or this is where you're starting, this is where you're ending. This is the before you studied the gas, then you either changed pressure or volume, and then this is the after, okay? And so if we're given 3 of the 4 variables here, we can solve for the last one. And so I kind of already said this, if volume decreases, pressure increases, and vice versa. Conceptually, it is important to know that this just looks at pressure and volume change, but you have to hold temperature the same. So notice in that 2-liter bottle, we didn't change the temperature. The temperature of the gas was the same throughout. And then also, you have to have a flexible container, since volume is one of the variables that you are studying, okay? So temperature can't change, because otherwise it would be in this equation, and then volume, the container has to be flexible, okay? If we want to look at a conceptual model of this, I feel like the lab does a good job, but again, just to kind of highlight this, if you have, so this would be like your before, okay, so you have a certain number of particles, so also the number of particles is staying the same. So I have 1, 2, 3, 4, 5, 1, 2, 3, 4, 5 in both containers, but this is the before, okay, and this is the after. So we could measure in the before the pressure and the volume, And then if we were to decrease the volume here, so now these gases occupy less space, we'd expect the pressure to go up because now the particles are going to slam into the walls of their container more often. And if you have more collisions, you have a higher pressure. And vice versa. If if we went from this picture back to this one, if we were to increase the volume, the pressure would go down because the particles wouldn't hit the walls of their container as often. I'm going to do a mathematical problem so that you have this to kind of view how we would solve one of these problems on a homework or a lab when we put numbers to it, which we will starting soon. So this problem says, what is the final pressure of a gas if it is initially at 2 atmospheres and the volume is changed from 42 to 124. So I'm going to highlight the before stuff in yellow. So those numbers are linked, and it doesn't really matter what we make the ones and the twos. I will always make my ones kind of the before or the initial conditions and my twos the final. But because it only mentions pressure and volume and it talks about constant temperature, meaning temperature is not changing, then this would be the equation that I would use. And I think it's a really good idea to list. This is our initial pressure, and it's linked to this volume, and this is our second volume, and it wants to know final pressure. So we're looking for P2 here. I always want to see the variable that you are solving for isolated. And so that means moving all the other variables to the other side of the equation before you do any numbers. So I don't want you to put your numbers in and then just solve it. I want to see unit cancellation. So in order to rearrange this equation with P2 by itself on both sides, I need to move V2 to the other side. So I'm going to divide both sides by V2. It will cancel on this side. So then the final pressure will be the initial pressure times the initial volume divided by the final volume. Then I'm going to do a number setup. So my initial pressure is 2.0 atmospheres. I'm going to multiply that by my initial volume of 42 liters, and I'm going to divide that by 124 liters. You need numbers with units. If you just have 242 and 124, I have no idea what you're talking about. I will not give you full credit. This shows liters cancels. The only thing that does not is atmospheres, which should make sense since we are solving for pressure. So mathematically, I'm going to take 2 times the 42 and then divide by 124. And I'm going to get a final pressure of 0.6. It says 0.6774, etc. on your calculator, but with only 2 sig figs, since I have 2 in this one, 2 and 3, I'm just multiplying, dividing, so I'm going to keep the least amount. I'm just going to get 0.68 atmospheres. And you can check, does this seem reasonable? We went from a smaller volume to a higher volume, so volume was increasing, which means pressure should decrease, and our pressure started at 2, ended at 0.68, so that seems reasonable. It's always good to check, does my answer seem reasonable? Charles' law. That was the station 2. That's where you heated a flask on the hot plate with a balloon on it, and as you heated it, so as the temperature increased, the volume increased, the balloon got bigger, and vice versa. As the temperature decreased at the end, you let it cool down, the balloon shrank, and so temperature decreased. And that is a linear, a direct relationship, proportional relationship. Graphically, if you had temperature and volume, as one goes up, the other goes up linearly. Mathematically, if you have a linear relationship, this is how the equation would look. So it's a little different than Boyle's law, but you have volume over temperature, V1 divided by T1 is equal to V2 over T2. That's how you set up a direct relationship. So if temperature increases, volume increases, and vice versa. This is going to look at how temperature of a gas affects volume, but you have to keep pressure and amount constant, so they can't be changing. You also have to have a flexible container since volume is one of the variables in the equation. So you have to have a container like you did with the balloon, a flexible container, or like you had with Boyle's law with that gas being compressed with the water. You absolutely have to have temperature in Kelvin in order to plug in any values into that equation. And then how do we explain this? Relationship, what's happening to the particles. The easiest way to do this is just to think like, remember, temperature is related to kinetic energy. If particles have more kinetic energy, that means they're moving faster. They're going to have, they would also have more force to push on the walls of the container. But since the walls of the container are flexible, they would give to that force. It's going to push the walls of the container out and have more space. And that's how you keep pressure the same in that kind of a situation, since we're changing temperature here. And then overall have a larger volume. To do a mathematical problem for this. So I'm going to solve this problem here. So we have a gas is placed in a 2-liter flexible container at 23.5 degrees Celsius. The container is heated to 50.3. How much space? It's talking about volume. So whenever I see a variable, I'm going to list a number. I'm going to list with variables. So 2.0 liters is a volume. That's an initial volume. Degrees Celsius is a variable for temperature. So the 2 liters is associated with the 21.3. It says it's heated, so this is like above after. So we're changing the temperature, measuring it, and then seeing what would the final volume be. So it only mentions volume and temperature. So I write down Charles' law, V1 over T1 equals V2 over T2. And I am solving for V2, this variable right here, which means I need to isolate it before. So I need to isolate the variable before I put any numbers into my equation. Hear me say that again. So that means I need to move T2, need to move it out of the denominator. In order to do that, I would need to multiply both sides by T2. It will cancel if I do that on the right. So then V2 rearranged is going to be T2 times V1 over T1. And then I can do a number setup, okay? The other thing I need to do here is I need to change my temperatures. As soon as I see them in degrees Celsius, I need to convert them to Kelvin. So T1, I'm going to add 273 to both of these to get my temperature. It's a plus 23. And then my T2, the 50.3 plus the 273. And get both of those in Kelvin right away. You do not want to ever leave them in Celsius. As soon as you see them, convert them to Kelvin. So we've got 296.5 Kelvin for temperature 1, and then for temperature 2, we've got 323.3 Kelvin. All right, so now I can do a number setup. So T2, one of the most common errors I see is students plug in the wrong number, so always label them in your problem and then put them in accordingly. So T2 is going to be so volume 2 is equal to temperature 2, which is the 323.3 Kelvin, times volume 1, which is the only volume in our problem, which was 2 liters, 2.00 liters. That's over temperature 1, which is our 296.5 Kelvin. And then hopefully you can see Kelvin cancels. The only unit that doesn't is liters. And when I solve for this, 323.3 multiplied by 2, and then I divide it by 296.5, I'm going to get 2.18 liters. Temperature went up, so volume should go up. It went up a little bit. The last relationship that we looked at in our early gas law lab was station 3, and it's called Gay-Lussac's law. And this looks at temperature and pressure. So what happened in station 3, you had that temperature pressure gauge, you had a fixed volume container, okay, in that absolute zero device. So you had that sphere, and then you had the temperature gauge, but it was a rigid container. So there was a gas in here, but it was a fixed gas. And so what you saw was as you increased the temperature, the pressure increased, or vice versa. as temperature decreased, pressure decreased. That is, again, that's a direct mathematical relationship. And as one variable goes up, the other goes up. So graphically, it would be a linear line. The equation for this should look similar to Charles' law, except that it's pressure over temperature equals pressure 2 and temperature 2 at a second set of conditions. And this is going to look at pressure and temperature, but you have to keep volume and amount of gas particles held constant, which means you have to have a rigid container like you did in station 3. You had that fixed container, inflexible, wasn't going to change sizes. That's the only way you can take volume out of the equation. So again, if pressure increases, then the temperature increases. Conceptually, again, what's happening to the particles here? How can we explain this? So if you increase the temperature, then you are increasing the kinetic energy. The particles are going to move faster, and they're going to have more kinetic energy. So they're going to hit the walls of the container more often, and with more energy. And since pressure is created when particles hit the walls of the container and with how much force they hit the containers, the pressure would increase. And because volume is staying constant, so it's not a flexible container, so the pressure will go up. If the container is flexible and when the particles hit the walls of the container can get bigger, then pressure remains the same. But if the container cannot change sizes, that's when the pressure goes up. And so then there's a nice little graph of showing Gay-Lussac's law. A mathematical problem for this, just to show you an example, so you have this to refer to. So here we have a gas has a pressure of 0.370 atmospheres. So this is our pressure 1, and it's at a certain temperature. I'm going to add 273 to it immediately and get my 323 here, Kelvin. I don't want to see it in degrees Celsius at all. This is going to be my T1. And it wants to know what is the new temperature if the pressure is at 1.01. So P2 is that. So I hear pressure and temperature, no mention of volume. So I'm going to use P1 over T1 equals P2 over T2. Now this time we want to solve for T2. That's what the problem states. And this variable is in the denominator. And if you don't know how to rearrange an equation with the variable that you're solving for when it's in the denominator, you cannot just divide both sides by P2 because then your T2 is still in the denominator. So if you're ever solving for T2, you're going to cross multiply your equation and rewrite it. So I'm going to rewrite it as P1 times T2 is equal to T1 times P2. And then I still want to solve for T2. So I'm going to move my P1 to the other side. So I'm going to divide both sides by P1. It will cancel on this side. So rearrange, T2 is going to be T1 times P2 over P1. That's going to be the equation rearranged. So now I can do a number setup here with my unit. So temperature 2 is going to be my 323 Kelvin times pressure 2. Okay, so make sure you select the right one. Pressure 2 is the 1.01 atmospheres. This is why it's really important to read the problem and then make sure you plug in the numbers in the right place. And then the initial pressure was the 0.370 atmospheres here. And you should be able to predict. Pressure went up, so temperature should go up. So type in 323 times 1.01 in my calculator, then divide that by 0.370. And I'm going to get a temperature. In my calculator, it's going to read 881.70, etc. I need to round that to 3 sig figs, since all of these numbers have 3 from the initial. So 882 Kelvin would be my new temperature, which seems reasonable since I increased the pressure. The temperature should also increase. these are just some sample problems. We will do more, and we also learn about what the combined gas law is in class. But this should at least show you some of the mathematical problems that you're going to be asked to do, and then you have this in your pocket if you need to rewatch it. So you have some sample problems of the kind of the three relationships of the variables, looking at pressure and volume, volume and temperature, pressure and temperature. Notice in all of these, the amount of gas was held constant, and then one of the other variables was removed from the equation, like it wasn't involved in the equation. That's going to be important for next future lessons revolving around gas laws and when we're looking at them qualitatively and quantitatively.